other physicists that there was in fact no singularity at the beginning of the universe. As we shall see later, it can disappear once quantum effects are taken into account. We have seen in this chapter how in less than half a century, man's view of the universe, formed over millennia, has been transformed. Hubble's discovery that the universe was expanding and the realization of the insignificance of our own planet in the vastness of the universe were just the starting point. As experimental and theoretical evidence mounted, it became more and more clear that the universe must have had a beginning in time, until, in 1970, this was finally proved by Penrose and myself on the basis of Einstein's general theory of relativity. That proof showed that general relativity is only an incomplete theory. It cannot tell us how the universe started off, because it predicts that all physical theories, including itself, break down at the beginning of the universe. However, general relativity claims to be only a partial theory. So what the singularity theorems really show is that there must have been a time in the very early universe when the universe was so small that one could no longer ignore the small-scale effects of the other great partial theory of the 20th century, quantum mechanics. At the start of the 1970s, we were forced to turn then our search for an understanding of the universe from our theory of the extraordinarily vast to our theory of the extraordinarily tiny. That theory, quantum mechanics, will be described next, before we turn to the efforts to combine the two partial theories into a single quantum theory of gravity. Chapter 4, The Uncertainty Principle.
Okay, we got it, guys.
The success of scientific theories, particularly Newton's theory of gravity, led the French scientist, the Marquis de Laplace, at the beginning of the 19th century to argue that the universe was completely deterministic. Laplace suggested that there should be a set of scientific laws that would allow us to predict everything that would happen in the universe, if only we knew the complete state of the universe at one time. For example, if we knew the positions and speeds of the sun and the planets at one time, then we could use Newton's laws to calculate the state of the solar system at any other time. Determinism seems fairly obvious in this case, but Laplace went further to assume that there were similar laws governing everything else, including human behavior. The doctrine of scientific determinism was strongly resisted by many people who felt that it infringed God's freedom to intervene in the world, but it remained the standard assumption of science until the early years of this century. One of the first indications that this belief would have to be abandoned came when calculations by the British scientists Lord Rayleigh and Sir James Jeans suggested that a hot object or body such as a star must radiate energy at an infinite rate. According to the laws we believed at the time, a hot body ought to give off electromagnetic waves such as radio waves, visible light, or X-rays equally at all frequencies. For example, a hot body should radiate the same amount of energy in waves with frequencies between 1 and 2 million waves a second, as in waves with frequencies between 2 and 3 million waves a second. Now, since the number of waves a second is unlimited, this would mean that the total energy radiated would be infinite. In order to avoid this obviously ridiculous result, the German scientist Max Planck suggested in 1900 that light, X-rays, and other waves could not be emitted at an arbitrary rate, but only in certain packets that he called quanta. Moreover, each quantum had a certain amount of energy that was greater the higher the frequency of the waves. So at a higher enough frequency, the emission of a single quantum would require more energy than was available. Thus, the radiation at high frequencies would be reduced, and so the rate at which the body lost energy would be finite. The quantum hypothesis explained the observed rate of emission of radiation from hot bodies very well, but its implications for determinism were not realized until 1926, when another German scientist, Werner Heisenberg, formulated his famous uncertainty principle. In order to predict the future position and velocity of a particle, one has to be able to measure its present position and velocity accurately. The obvious way to do this is to shine light on the particle. Some of the waves of light will be scattered by the particle, and this will indicate its position. However, one will not be able to determine the position of the particle more accurately than the distance between the wave crests of light, so one needs to use light of a short wavelength in order to measure the position of the particle precisely. Now, by Planck's quantum hypothesis, one cannot use an arbitrarily small amount of light. One has to use at least one quantum. This quantum will disturb the particle and change its velocity in a way that cannot be predicted. Moreover, the more accurately one measures the position, the shorter the wavelength of the light that one needs, and hence the higher the energy of a single quantum. So the velocity of the particle will be disturbed by a larger amount. In other words, the more accurately you try to measure the position of the particle, the less accurately you can measure its speed, and vice versa. Heisenberg showed that the uncertainty in the position of the particle times the uncertainty in its velocity times the mass of the particle can never be smaller than a certain quantity, which is known as Planck's constant. Moreover, this limit does not depend on the way in which one tries to measure the position or velocity of the particle, or on the type of particle. Heisenberg's uncertainty principle is a fundamental, inescapable property of the world. The uncertainty principle had profound implications for the way in which we view the world. Even after more than 50 years, they've not been fully appreciated by many philosophers, and they are still the subject of much controversy. The uncertainty principle signaled an end to Laplace's dream of a theory of science, a model of the universe that would be completely deterministic. One certainly cannot predict future events exactly if one cannot even measure the present state of the universe precisely. We could still imagine that there is a set of laws that determines events completely for some supernatural being who could observe the present state of the universe without disturbing it. However, such models of the universe are not of much interest to us ordinary mortals. It seems better to employ the principle of economy known as Occam's razor and cut out all the features of the theory that cannot be observed. This approach led Heisenberg, Erwin Schrödinger, and Paul Dirac in the 1920s to reformulate mechanics into a new theory called quantum mechanics, based on the uncertainty principle. In this theory, particles no longer had separate, well-defined positions and velocities that could not be observed. Instead, they had a quantum state, which was a combination of position and velocity. In general, quantum mechanics does not predict a single definite result for an observation. Instead, it predicts a number of different possible outcomes and tells us how likely each of these is. That is to say, if one made the same measurement on a large number of similar systems, each of which started off in the same way, one would find that the result of the measurement would be A in a certain number of cases, B in a different number, and so on. One could predict the approximate number of times that the result would be A or B, but one could not predict the specific result of an individual measurement. Quantum mechanics, therefore, introduces an unavoidable element of unpredictability or randomness into science.
I'm listening
Einstein
to the
objected
audiobook
to this
right
very
now,
strongly,
taking it in.
despite the important role
I'm
he
gonna
had
make
played
a
in the development
comment
of the
in a little
ideas.
bit
Einstein was awarded the Nobel Prize for his contribution
when
to
I get
quantum
this
theory.
bus to
Nevertheless,
the place it needs to be.
Einstein never accepted that the universe was governed by chance. His feelings were summed up in his most famous statement: God does not play dice. Most other scientists, however, were willing to accept quantum mechanics because it agreed perfectly with experiment. Indeed, it has been an outstandingly successful theory and underlies nearly all of modern science and technology. It governs the behavior of transistors and integrated circuits, which are the essential components of electronic devices such as TVs and computers, and is also the basis of modern chemistry and biology. The only areas of physical science into which quantum mechanics has not yet been properly incorporated are gravity and the large-scale structure of the universe. Although light is made up of waves, Planck's quantum hypothesis tells us that in some ways it behaves as if it were composed of particles. It can be emitted or absorbed only in packets or quanta. Equally, Heisenberg's uncertainty principle implies that particles behave in some respects like waves. They do not have a definite position, but they are smeared out with a certain probability distribution. The theory of quantum mechanics is based on an entirely new type of mathematics that no longer describes the real world in terms of particles and waves. It is only the observations of the world that may be described in those terms. There is, thus, a duality between waves and particles in quantum mechanics. For some purposes, it's helpful to think of particles as waves, and for other purposes, it is better to think of waves as particles. An important consequence of this is that one can observe what is called interference between two sets of waves or particles. That is to say, the crests of one set of waves may coincide with the troughs of the other set. The two sets of waves then cancel each other out, rather than adding up to a stronger wave as one might expect. A familiar example of interference in the case of light is the colors that are often seen in soap bubbles. Now, these are caused by reflection of light from the two sides of the thin film of water forming the bubble. White light consists of light waves of all different wavelengths, or colors. For certain wavelengths, the crests of the waves reflected from one side of the soap film coincide with the troughs reflected from the other side. The colors corresponding to these wavelengths are absent from the reflected light, which therefore appears to be colored. Interference can also occur for particles because of the duality introduced by quantum mechanics. A famous example is the so-called two-slit experiment. Consider a partition with two narrow parallel slits in it. On one side of the partition, one places a source of light of a particular color, that is, of a particular wavelength. Most of the light will hit the partition, but a small amount will go through the slits. Now, suppose one places a screen on the far side of the partition from the light. Any point on the screen will receive waves from the two slits. However, in general, the distance the light has to travel from the source to the screen via the two slits will be different. This will mean that the waves from the slits will not be in phase with each other when they arrive at the screen. In some places, the waves will cancel each other out, and in others, they will reinforce each other. The result is a characteristic pattern of light and dark fringes. The remarkable thing is that one gets exactly the same kind of fringes if one replaces the source of light by a source of particles, such as electrons, with a definite speed. This means that the corresponding waves have a definite length. It seems the more peculiar because if one only has one slit, one does not get any fringes, just a uniform distribution of electrons across the screen. One might therefore think that opening another slit would just increase the number of electrons hitting each point of the screen. But because of interference, it actually decreases it in some places. If electrons are sent through the slits one at a time, one would expect each to pass through one slit or the other, and so behave just as if the slit it passed through were the only one there, giving a uniform distribution on the screen. In reality, however, even when the electrons are sent one at a time, the fringes still appear. Each electron, therefore, must be passing through both slits at the same time. The phenomenon of interference between particles has been crucial to our understanding of the structure of atoms, the basic units of chemistry and biology, and the building blocks out of which we and everything around us are made. At the beginning of this century, it was thought that atoms were rather like the planets orbiting the sun, with electrons, particles of negative electricity, orbiting around a central nucleus, which carried positive electricity. The attraction between the positive and negative electricity was supposed to keep the electrons in their orbits in the same way that the gravitational attraction between the sun and the planets keeps the planets in their orbits. Now, the trouble with this was that the laws of mechanics and electricity before quantum mechanics predicted that the electrons would lose energy and so spiral inward until they collided with the nucleus. This would mean that the atom, and indeed all matter, should rapidly collapse to a state of very high density. A partial solution to the problem was found by the Danish scientist Niels Bohr in 1913. He suggested that maybe the electrons were not able to orbit at just any distance from the central nucleus, but only at certain specified distances. If one also supposed that only one or two electrons could orbit at any one of these distances, this would solve the problem of the collapse of the atom, because the electrons could not spiral in any further than to fill up the orbits with the least distances and energies. This model explained quite well the structure of the simplest atom, hydrogen, which was only one electron orbiting around the nucleus, but it was not clear how one ought to extend it to more complicated atoms. Moreover, the idea of a limited set of allowed orbits seemed very arbitrary. The new theory of quantum mechanics resolved the difficulty. It revealed that an electron orbiting around the nucleus could be thought of as a wave with a wavelength that depended on its velocity. For certain orbits, the length of the orbit would correspond to a whole number, as opposed to a fractional number of wavelengths of the electron. For these orbits, the wave crest would be in the same position each time round, so the waves would add up. These orbits would correspond to Bohr's allowed orbits. However, for orbits whose lengths were not a whole number of wavelengths, each wave crest would eventually be cancelled out by a trough as the electrons went round. These orbits would not be allowed. A nice way of visualizing the wave-particle duality is the so-called sum over histories introduced by the American scientist Richard Feynman. In this approach, the particle is not supposed to have a single history or path in space-time as it would in a classical non-quantum theory. Instead, it's supposed to go from A to B by every possible path. With each path, there are associated a couple of numbers. One represents the size of a wave, and the other represents the position in the cycle.
Okay, guys. Well, what I have to say so far, just a second. Let me get up some music. So far, the book has been talking deeply about quantum physics and the sciences behind quantum mechanics when it comes to particles and all of that. They also talk about light. They also talk about light, and all of that is really interesting. They were getting into the prism and how color affects puddles, and they were talking about different scientists and their conclusions, and they were talking about Albert Einstein and Niels Bohr. And if I'm sure there's things that Stephen Hawking knew about this universe that if you told it to a random person, they wouldn't believe it. They would call you loony. They would be like, you're crazy. And if they did believe you, they would be so afraid. They would be so afraid. Stephen Hawking believed that AI was going to take over in the future, just a complete AI takeover, which I don't think an AI takeover is going to happen as much as a planetary meteor would hit the Earth. But, you know, I don't know what Stephen Hawking knows. I'm sure Stephen Hawking would look at everything in the universe as some kind of threat. You know, even gas in the galaxy could be a threat. A gas cloud just orbiting into our atmosphere, if that's even possible. Who knows? The universe is unending, right? Which, by the way, I'm very lucky. On a personal note, I am very lucky to have the woman that I have in my life. She is very intelligent. She is like a work wife. But yeah, I'm very, very lucky to have her. But anyway, sorry about that. I just want to get that out there. I want to get that off my chest. But listen, you know, it's like Pink Floyd Dark Side of the Moon. You know, when you go into quantum sciences, you get into magic, and then you get into all different industries. You get into the science industry, you get into the music industry, you get into the entertainment industry. You know, quantum mechanics is a pyramid. You know, you know, I heard Neil deGrasse Tyson say that quantum mechanics was like a party, you know, with great people. Somewhere he said that. But really it's more about being humble, and when it all comes down to the God particle, which is like the Philosopher's Stone of quantum mechanics, right? So you have to be humble. You have to do good for God. If someone took a chance on me and put me on the spot to be tested infinitely forever, if my whole existence is to be a litmus test, then it's to serve God. It's to serve God to get our species to different planets. Right? That's where it's at now. That's where we're at now. We have to get our species to different planets. It doesn't matter if you're Indian. It doesn't matter if you're black. It doesn't matter who you are. It doesn't matter what religion you are. We need to get to space. Right? And Stephen Hawking would agree with that. But anyway, I think I said enough about what I had to say on this topic. Let's continue with the book.
That is, whether it is at a crest or a trough. The probability of going from A to B is found by adding up the waves for all the paths. In general, if one compares a set of neighboring paths, the phases or positions in the cycle will differ greatly. This means that the waves associated with these paths will almost exactly cancel each other out.
That's an
However,
interesting
for
thought,
some sets of neighboring paths, the phase will not vary much between paths. The waves for these paths will not cancel out, so such paths correspond to Bohr's allowed orbits. With these ideas in concrete mathematical form, it was relatively straightforward to calculate the allowed orbits in more complicated atoms and even in molecules, which are made up of a number of atoms held together by electrons in orbits that go round more than one nucleus. Since the structure of molecules and their reactions with each other underlie all of chemistry and biology, quantum mechanics allows us, in principle, to predict nearly everything we see around us within the limits set by the uncertainty principle. In practice, however, the calculations required for systems containing more than a few electrons are so complicated that we cannot do them. Einstein's general theory of relativity seems to govern the large-scale structure of the universe. It is what is called a classical theory. That is, it does not take account of the uncertainty principle of quantum mechanics as it should for consistency with other theories. The reason that this does not lead to any discrepancy with observation is that all the gravitational fields that we normally experience are very weak. However, the singularity theorems discussed earlier indicate that the gravitational field should get very strong in at least two situations, black holes and the Big Bang. In such strong fields, the effects of quantum mechanics should be important. Thus, in a sense, classical general relativity, by predicting points of infinite density, predicts its own downfall, just as classical, that is, non-quantum mechanics, predicted its downfall by suggesting that atoms should collapse to infinite density. We do not yet have a complete, consistent theory that unifies general relativity and quantum mechanics, but we do know a number of the features it should have. The consequences that these would have for black holes and the Big Bang will be described in later chapters. For the moment, however, we shall turn to the recent attempts to bring together our understanding of the other forces of nature into a single unified quantum theory. Chapter 5, Elementary Particles and the Forces of Nature. Aristotle believed that all the matter in the universe was made up of four basic elements: earth, air, fire, and water. These elements were acted on by two forces: gravity, the tendency for earth and water to sink, and levity, the tendency for air and fire to rise. This division of the contents of the universe into matter and forces is still used today. Aristotle believed that matter was continuous. That is, one could divide a piece of matter into smaller and smaller bits without any limit. One never came up against a grain of matter that could not be divided further. A few Greeks, however, such as Democritus, held that matter was inherently grainy and that everything was made up of large numbers of various different kinds of atoms. The word atom means indivisible in Greek. For centuries, the argument continued without any real evidence on either side. But in 1803, the British chemist and physicist John Dalton pointed out that the fact that chemical compounds always combined in certain proportions could be explained by the grouping together of atoms to form units called molecules. However, the argument between the two schools of thought was not finally settled in favor of the atomists until the early years of this century. One of the important pieces of physical evidence was provided by Einstein. In a paper written in 1905, a few weeks before the famous paper on special relativity, Einstein pointed out that what was called Brownian relativity, or Brownian motion, the irregular random motion of small particles of dust suspended in a liquid, could be explained as the effect of atoms of the liquid colliding with the dust particles. By this time, there were already suspicions that these atoms were not, after all, indivisible. Several years previously, a fellow of Trinity College, Cambridge, J.J. Thomson, had demonstrated the existence of a particle of matter called the electron that had a mass less than 1,000th of that of the lightest atom. He used a setup rather like a modern TV picture tube. A red-hot metal filament gave off the electrons, and because these have a negative electric charge, an electric field could be used to accelerate them toward a phosphor-coated screen. When they hit the screen, flashes of light were generated. Soon it was realized that these electrons must be coming from within the atoms themselves. And in 1911, the British physicist Ernest Rutherford finally showed that the atoms of matter do have internal structure. They are made up of an extremely tiny, positively charged nucleus, around which a number of electrons orbit. He deduced this by analyzing the way in which particles, which are positively charged particles given off by radioactive atoms, are deflected when they collide with atoms. At first, it was thought that the nucleus of the atom was made up of electrons and different numbers of a positively charged particle called the proton. That's from the Greek word meaning first, because it was believed to be the fundamental unit from which matter was made. However, in 1932, a colleague of Rutherford's at Cambridge, James Chadwick, discovered that the nucleus contained another particle called the neutron, which had almost the same mass as a proton but no electrical charge. Chadwick received the Nobel Prize for this discovery and was elected Master of Gonville and Caius College, Cambridge, a college of which I am now a fellow. He later resigned as master because of a disagreement with the fellows. There had been a bitter dispute in the college ever since a group of young fellows returning after the war had voted many of the old fellows out of the college offices that they had held for a long time. This was before my time. I joined the college in 1965 at the tail end of the bitterness, when similar disagreements forced another Nobel Prize-winning master, Sir Neville Mott, to resign. Up to about 20 years ago, it was thought that protons and neutrons were elementary particles, but experiments in which protons were collided with other protons or electrons at high speeds indicated that they were in fact made up of smaller particles. These particles were named quarks by the Caltech physicist Murray Gell-Mann, who won the Nobel Prize in 1969 for his work on them. The origin of the name is an enigmatic quotation from James Joyce. 3 quarks for muster mark. The word quark is supposed to be pronounced like quart, but with a K at the end instead of a T. It is usually pronounced to rhyme with lark. There are a number of different varieties of quarks. There are thought to be at least 6 flavors, which we'll call up, down, strange, charmed, bottom, and top. Each flavor comes in 3 colors, red, green, and blue. It should be emphasized that these terms are just labels. Quarks are much smaller than the wavelength of visible light, and so do not have any color in the normal sense. It is just that modern physicists seem to have more imaginative ways of naming new particles and phenomena. They no longer restrict themselves to Greek. A proton, or a neutron, is made up of 3 quarks, 1 of each color. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down and 1 up. We can create particles made up of other quarks, strange, charmed, bottom and top. But these all have a much greater mass and decay very rapidly into protons and neutrons. We now know that neither the atoms nor the protons and neutrons within them are indivisible. So the question is, what are the truly elementary particles, the basic building blocks from which everything is made? Since the wavelength of light is much larger than the size of an atom, we cannot hope to look at the parts of an atom in the ordinary way. We need to use something with a much smaller wavelength. As we saw in the last chapter, quantum mechanics tells us that all particles are in fact waves, and that the higher the energy of a particle, the smaller the wavelength of the corresponding wave. So the best answer we can give to our question depends on how high a particle energy we have at our disposal, because this determines on how small a length scale we can look. These particle energies are usually measured in units called electron volts. In Thomson's experiments with electrons, we saw that he used an electric field to accelerate the electrons. The energy that an electron gains from an electric field of 1 volt is what is known as an electron volt. In the 19th century, when the only particle energies that people knew how to use were the low energies of a few electron volts generated by chemical reactions such as burning, it was thought that atoms were the smallest unit. In Rutherford's experiment, the particles, had energies of millions of electron volts. More recently, we have learned how to use electromagnetic fields to give particles energies of at first millions and then thousands of millions of electron volts. And so we know that particles that were thought to be elementary 20 years ago are in fact made up of smaller particles. May these, as we go to still higher energies, in turn be found to be made up from still smaller particles? This is certainly possible, but we do have some theoretical reasons for believing that we have, or are very near to, a knowledge of the ultimate building blocks of nature. Using the wave-particle duality discussed in
Alright guys, so basically so far in chapter 5, I'm just gonna cut it off there for a quick talk. Basically in chapter 5 he's talking about different universities and drama with the Nobel Peace Prize, and you know, how people have gotten turned away from the Nobel Peace Prize. And this has happened before. People have been, who deserve the Nobel Peace Prize, have been denied because they have said that people from different regions of the world are naturally different from people from other regions of the world. You know, when you get into eugenics and racial sciences, it's very, very, very controversial, which it shouldn't be, because there's many things that black men have and colored men have that white men don't have, right? And the same goes for Asians. There's many things that Asian men have that black men and white men don't have, right? And it goes the same thing for white men. White men, there's some things white men have that black men and Asian men don't have, right? So we have to get past these boundaries that prevent us from really accelerating in biological sciences. Instead of promising all of these mentally ill homosexuals they can be transsexual lesbians. Do you guys kind of get what I'm saying? I'm just being honest, guys. I'm sorry. But we have to be honest to ourselves when it comes to science, and I'm sure Stephen Hawking would say the same thing. But yeah. But then it started talking about how darn it. And then it started talking about his friends and his colleagues, and then how he was talking about pretty much the philosophy and of quantum theory and his personal life. So that's where we're at right now in chapter 5. But yeah, let's go ahead and keep going.
In the last chapter, everything in the universe, including light and gravity, can be described in terms of particles. These particles have a property called spin. One way of thinking of spin is to imagine the particles as little tops spinning about an axis. However, this can be misleading because quantum mechanics tells us that the particles do not have any well-defined axis. What the spin of a particle really tells us is what the particle looks like from different directions. A particle of spin 0 is like a dot. It looks the same from every direction. On the other hand, a particle of spin 1 is like an arrow. It looks different from different directions. Only if one turns it around a complete revolution, 360 degrees, does the particle look the same. A particle of spin 2 is like a double-headed arrow. It looks the same if one turns it round half a revolution, 180 degrees. Similarly, higher spin particles look the same if one turns them through smaller fractions of a complete revolution. All this seems fairly straightforward, but the remarkable fact is that there are particles that do not look the same if one turns them through just one revolution. You have to turn them through 2 complete revolutions. Such particles are said to have spin 1/2. All the known particles in the universe can be divided into 2 groups: particles of spin 1/2, which make up the matter in the universe, and particles of spin 0, 1, and 2, which we shall see give rise to forces between the matter particles. The matter particles obey what is called Pauli's exclusion principle. This was discovered in 1925 by an Austrian physicist, Wolfgang Pauli, for which he received the Nobel Prize in 1945. He was the archetype theoretical physicist. It was said of him that even his presence in the same town could make experiments go wrong. Pauli's exclusion principle says that two similar particles cannot exist in the same state. That is, they cannot have both the same position and the same velocity within the limits given by the uncertainty principle. The exclusion principle is crucial because it explains why matter particles do not collapse to a state of very high density under the influence of the forces produced by the particles of spin 0, 1, and 2. If the matter particles have very nearly the same positions, they must have different velocities, which means that they will not stay in the same position for long. If the world had been created without the exclusion principle, quarks would not form separate, well-defined protons and neutrons, nor would these, together with electrons, form separate, well-defined atoms. They would all collapse to form a roughly uniform, dense soup. A proper understanding of the electron and other spin half particles did not come until 1928, when a theory was proposed by Paul Dirac, who later was elected to the Lucasian Professorship of Mathematics at Cambridge, the same professorship that Newton had once held and that I now hold. Dirac's theory was the first of its kind that was consistent with both quantum mechanics and the special theory of relativity. It explained mathematically why the electron had spin half, that is, why it didn't look the same if you turned it through only one complete revolution, but did if you turned it through 2 revolutions. It is also predicted that the electron should have a partner, an anti-electron or positron. The discovery of the positron in 1932 confirmed Dirac's theory and led to his being awarded the Nobel Prize for Physics in 1933. We now know that every particle has an antiparticle with which it can annihilate. In the case of the force-carrying particles, the antiparticles are the same as the particles themselves. There could be whole anti-worlds and anti-people made out of antiparticles. However, if you meet yourself or your anti-self, don't shake hands. You would both vanish in a great flash of light.
Oh my goodness.
The question of why there seem to be so many more particles than antiparticles around us is extremely important, and I shall return to it later in the chapter. In quantum mechanics, the forces or interactions between matter particles are all supposed to be carried by particles of integer spin, 0, 1, or 2. What happens is that a matter particle, such as an electron or a quark, emits a force-carrying particle. The recoil from this emission changes the velocity of the matter particle. The force-carrying particle then collides with another matter particle and is absorbed. This collision changes the velocity of the second particle, just as if there had been a force between the two matter particles. It is an important property of the force-carrying particles that they do not obey the exclusion principle. Now, this means that there is no limit to the number that can be exchanged, and so they can give rise to a strong force. However, if the force-carrying particles have a high mass, it will be difficult to produce and exchange them over a large distance. So the forces that they carry will have only a short range. On the other hand, if the force-carrying particles have no mass of their own, the forces will be long-range. The force-carrying particles exchanged between matter particles are said to be virtual particles because, unlike real particles, they cannot be directly detected by a particle detector. We know they exist because they do have a measurable effect. They give rise to forces between matter particles. Particles of spin 0, 1, or 2 do also exist in some circumstances as real particles when they can be directly detected. They then appear to us as what a classical physicist would call waves, such as waves of light or gravitational waves. They may sometimes be emitted when matter particles interact with each other by exchanging virtual force-carrying particles. For example, the electric repulsive force between two electrons is due to the exchange of virtual photons, which can never be directly detected. But if one electron moves past another, real photons may be given off, which we detect as light waves. Force-carrying particles can be grouped into 4 categories according to the strength of the force that they carry and the particles with which they interact. It should be emphasized that this division into 4 classes is man-made. It is convenient for the construction of partial theories, but it may not correspond to anything deeper. Ultimately, most physicists hope to find a unified theory that will explain all 4 forces as different aspects of a single force. Indeed, many would say this is the prime goal of physics today. Recently, successful attempts have been made to unify 3 of the 4 categories of force, and I shall describe these in this chapter. The question of the unification of the remaining category, gravity, we shall leave till later. The first category is the gravitational force. This force is universal. That is, every particle feels the force of gravity according to its mass or energy. Gravity is the weakest of the 4 forces by a long way. It is so weak that we would not notice it at all were it not for 2 special properties that it has. It can act over large distances, and it is always attractive. This means that the very weak gravitational forces between the individual particles in 2 large bodies, such as the Earth and the Sun, can all add up to produce a significant force. The other 3 forces are either short range or are sometimes attractive and sometimes repulsive, so they tend to cancel out. In the quantum mechanical way of looking at the gravitational field, the force between 2 matter particles is pictured as being carried by a particle of spin 2 called the gravitron. This has no mass of its own, so the force that it carries is long range. The gravitational force between the Sun and the Earth is ascribed to the exchange of gravitons between the particles that make up these 2 bodies. Although the exchanged particles are virtual, they certainly do produce a measurable effect. They make the Earth orbit the Sun. Real gravitons make up what classical physicists would call gravitational waves, which are very weak and so difficult to detect that they have never yet been observed. The next category is the electromagnetic force, which interacts with electrically charged particles like electrons and quarks, but not with uncharged particles such as gravitons. It is much stronger than the gravitational force. The electromagnetic force between 2 electrons is about a million. That is 1 with 42 zeros after it times bigger than the gravitational force. However, there are 2 kinds of electric charge, positive and negative. The force between 2 positive charges is repulsive, as is the force between 2 negative charges. But the force is attractive between a positive and a negative charge. A large body, such as the Earth or the Sun, contains nearly equal numbers of positive and negative charges. Thus, the attractive and repulsive forces between the individual particles nearly cancel each other out, and there is very little net electromagnetic force. However, on the small scales of atoms and molecules, electromagnetic forces dominate. The electromagnetic attraction between negatively charged electrons and positive charged protons in the nucleus causes the electrons to orbit the nucleus of the atom, just as gravitational attraction causes the Earth to orbit the Sun. The electromagnetic attraction is pictured as being caused by the exchange of large numbers of virtual massless particles of spin 1 called photons. Again, the photons that are exchanged are virtual particles. However, when an electron changes from one allowed orbit to another one nearer to the nucleus, energy is released and a real photon is emitted, which can be observed as visible light by the human eye if it has the right wavelength, or by a photon detector such as photographic film. Equally, if a real photon collides with an atom, it may move an electron from an orbit nearer the nucleus to one farther away. This uses up the energy of the photon, so it is absorbed. The third category is called the weak nuclear force, which is responsible for radioactivity and which acts on all matter particles of spin half, but not on particles of spin 0, 1, or 2, such as photons and gravitons. The weak nuclear force was not well understood until 1967, when Abdus Salam at Imperial College London and Stephen Weinberg at Harvard both proposed theories that unified this interaction with the electromagnetic force, just as Maxwell had unified electricity and magnetism about 100 years earlier. They suggested that in addition to the photon, there were three other spin-1 particles known collectively as massive vector bosons that carried the weak force. These are called W+, W-, and Z0, and each had a mass of around 100 GeV. GeV
Their
stands
accuracy
for
is
giga
incredible. I can't
electron
even
volt,
pay
or
attention to the
1,000
stuff
million
difficult.
electron volts. The Weinberg-Salam theory exhibits a property known as spontaneous symmetry breaking. This means that what appear to be a number of completely different particles at low energies are in fact found to be all the same type of particle, only in different states. At high energies, all these particles behave similarly. The effect is rather like the behavior of a roulette ball on a roulette wheel. At high energies, when the wheel is spun quickly, the ball behaves in essentially only one way. It rolls round and round, but as the wheel slows, the energy of the ball decreases, and eventually the ball drops into one of the 37 slots in the wheel. In other words, at low energies, there are 37 different states in which the ball can exist. If, for some reason, we could only observe the ball at low energies, we would then think that there were 37 different types of balls. In the Weinberg-Salam theory, at energies much greater than 100 GeV, the three new particles and the photon would all behave in a similar manner. But at the lower particle energies that occur in most normal situations, this symmetry between the particles would be broken. W+, W-, and Z0 would acquire large masses, making the forces they carry have a very short range. At the time that Salam and Weinberg proposed the theory, few people believed them, and particle accelerators were not powerful enough to reach the energies 100 GeV required to produce the real W+, W-, or Z0 particles. However, over the next 10 years or so, the other predictions of the theory at lower energies agreed so well with experiments that in 1979, Salam and Weinberg were awarded the Nobel Prize for Physics together with Sheldon Glashow, also at Harvard, who had suggested similar unified theories of the electromagnetic and weak nuclear forces. The Nobel Committee was spared the embarrassment of having made a mistake by the discovery in 1983 at CERN, the European Center for Nuclear Research, of the three massive partners of the photon with the correct predictive masses and other properties. Carlo Rubbia, who led the team of several hundred physicists that made the discovery, received the Nobel Prize in '84, along with Simon von der Meer, the CERN engineer who developed the antimatter storage system employed. It's very difficult to make a mark in experimental physics these days unless you are already at the top. The fourth category is the strong nuclear force, which holds the quarks together in the proton and neutron, and holds the protons and neutrons together in the nucleus of an atom. It is believed that this force is carried by another spin-1 particle
We
called
made
the
it just
gluon,
by the skin of our
which
teeth.
interacts only with itself and with the quarks. The strong nuclear force has a curious property called confinement. It always binds particles together in combinations that have no color. One cannot have a single quark on its own because it would have a color, red, green, or blue. Instead, a red quark has to be joined to a green and a blue quark by a string of gluons. Red plus green plus blue equals white. Such a triplet consists or constitutes a proton or a neutron. Another possibility is a pair consisting of a quark and an antiquark. Red plus anti-red, or green plus anti-green, or blue plus anti-blue equals white. Such combinations make up the particles known as mesons, which are unstable because the quark and the antiquark can annihilate each other, producing electrons and other particles. Similarly, confinement prevents one having a single gluon its own, because gluons also have color. Instead, one has to have a collection of gluons whose colors add up to white. Such a collection forms an unstable particle called a glue ball. The fact that confinement prevents one from observing an isolated quark or gluon might seem to make the whole notion of quarks and gluons as particles somewhat metaphysical. However, there is another property of the strong nuclear force called asymptotic freedom. It makes the concept of quarks and gluons well defined. At normal energies, the strong nuclear force is indeed strong, and it binds the quarks tightly together. However, experiments with large particle accelerators indicate that at high energies, the strong force becomes much weaker, and the quarks and gluons behave almost like free particles. Several almost free quarks were produced and gave rise to the jets of tracks that you'll see in the picture in my book. The success of the unification of the electromagnetic and weak nuclear forces led to a number of attempts to combine these two forces with the strong nuclear force into what is called a grand unified theory, or GUT. This title is rather an exaggeration. The resultant theories are not all that grand, nor are they fully unified, as they do not include gravity. Nor are they really complete theories, because they contain a number of parameters whose values cannot be predicted from the theory, but have to be chosen to fit in with an experiment. Nevertheless, they may be a step toward a complete, fully unified theory. The basic idea of guts is as follows. As we mentioned above, the strong nuclear force gets weaker at high energies. On the other hand, the electromagnetic and weak forces, which are not asymptotically free, get strong at high energies. At some very high energy, called the grand unification energy, these three forces would all have the same strength, and so could just be different aspects of a single force. The guts also predict that at this energy, the different spin half-matter particles like quarks and electrons would also all be essentially the same, thus achieving another unification. The value of the grand unification energy is not very well known, but it would probably have to be at least 1,000 million GeV. The present generation of particle accelerators can collide particles at energies of about 100 GeV, and machines are planned that would raise this to a few thousand GeV. But a machine that was powerful enough to accelerate particles to the grand unification energy would have to be as big as the solar system, and would be unlikely to be funded in the present economic climate. Thus, it is impossible to test grand unified theories directly in the lab. However, just as in the case of the electromagnetic and weak unified theory, there are low-energy consequences of the theory that can be tested. The most interesting of these is the prediction that protons, which make up much of the mass of ordinary matter, can spontaneously decay into lighter particles such as anti-electrons. The reason this is possible is that at the grand unification energy, there is no essential difference between a quark and an anti-electron. The three quarks inside a proton normally do not have enough energy to change into anti-electrons, but very occasionally one of them may acquire sufficient energy to make the transition, because the uncertainty principle means that the energy of the quarks inside the proton cannot be fixed exactly. The proton would then decay. The probability of a quark gaining sufficient energy is so low that one is likely to have to wait at least 1 million years. That's 1 followed by 30 zeros. This is much longer than the time since the Big Bang, which is a mere 10,000 million years, or thereabouts. That's 1 followed by 10 zeros. Thus, one might think that the possibility of spontaneous proton decay could not be tested experimentally. However, one can increase one's chances of detecting a decay by observing a large amount of matter containing a very large number of protons. If, for example, one observed a number of protons equal to 1 followed by 31 zeros for a period of 1 year, one would expect, according to the simplest gut, to observe more than 1 proton decay. A number of such experiments have been carried out, but none have yielded definite evidence of proton or neutron decay. One experiment used 8,000 tons of water and was performed in the molten salt mine in Ohio to avoid other events taking place caused by cosmic rays that might be confused with proton decay. Since no spontaneous proton decay had been observed during the experiment, one can calculate that the probable life of the proton must be greater than 10 million years. In other words, 1 with 31 zeros. This is longer than the lifetime predicted by the simplest grand unified theory. but there are more elaborate theories in which the predicted lifetimes are longer. Still more sensitive experiments involving even larger quantities of matter will be needed to test them. Even though it's very difficult to observe spontaneous proton decay, it may be that our very existence is a consequence of the reverse process, the production of protons, or more simply, of quarks, from an initial situation in which there were no more quarks than antiquarks, which is the most natural way to imagine the universe starting out. Matter on the Earth is made up mainly of protons and neutrons, which in turn are made up of quarks. There are no antiprotons or antineutrons made up from antiquarks, except for a few that physicists produce in large particle accelerators. We have evidence from cosmic rays that the same is true for all the matter in our galaxy. There are no antiprotons or antineutrons apart from a small number that are produced as particle-antiparticle pairs in high-energy collisions. If there were large regions of antimatter in our galaxy, we would expect to observe large quantities of radiation from the borders between the regions of matter and antimatter, where many particles will be colliding with their antiparticles, annihilating each other, and giving off high-energy radiation. We have no direct evidence as to whether the matter in other galaxies is made up of protons and neutrons or antiprotons and antineurons, but it must be one or the other. There cannot be a mixture in a single galaxy, because in that case, we would again observe a lot of radiation from annihilations. We therefore believe that all galaxies are composed of quarks rather than antiquarks, and it seems implausible that some galaxies should be matter and some should be antimatter. Why should there be so many more quarks than antiquarks? Why are there not equal numbers of each? It is certainly fortunate for us that the numbers are unequal, because if they had been the same, nearly all the quarks and antiquarks would have annihilated each other in the early universe and left a universe filled with radiation but hardly any matter. There would then have been no galaxies, stars, or planets on which human life could have developed. Luckily, grand unified theories may provide an explanation of why the universe should now contain more quarks than antiquarks, even if it started out with equal numbers of each. As we've seen, guts allow quarks to change into anti-electrons at high energy. They also allow the reverse processes, antiquarks turning into electrons, and electrons and anti-electrons turning into antiquarks and quarks. There was a time in the very early universe when it was so hot that the particle energies would have been high enough for these transformations to take place. But why should that lead to more quarks than antiquarks? The reason is that the laws of physics are not quite the same for particles and antiparticles. Up to 1956, it was believed that the laws of physics obeyed each of three separate symmetries called CP and T. The symmetry C means that the laws are the same for particles and antiparticles. The symmetry P means that the laws are the same for any situation and its mirror image. The mirror image of a particle spinning in a right-handed direction is one spinning in a left-handed direction. The symmetry T means that if you reverse the direction of motion of all particles and antiparticles, the system should go back to what it was at earlier times. In other words, the laws are the same in the forward and the backward directions of time. In 1956, two American physicists, Zhong Dao Li and Chen Ying-yang, suggested that the weak force does not in fact obey the symmetry P. In other words, the weak force would make the universe develop in a different way from the way in which the mirror image of the universe would develop. That same year, a colleague, Xianxin Wu, proved their prediction correct. She did this by lining up the nuclei of radioactive atoms in a magnetic field so that they were all spinning in the same direction, and showed that the electrons were given off more in one direction than another. The following year, Li and Yang received the Nobel Prize for their idea. It was also found that the weak force did not obey the symmetry C. That is, it would cause a universe composed of antiparticles to behave differently from our universe. Nevertheless, it seemed that the weak force did obey the combined symmetry CP. That is, the universe would develop in the same way as its mirror image if, in addition, every particle was swapped with its antiparticle. However, in 1964, two more Americans, J.W. Cronin and Val Fitch, discovered that even the CP symmetry was not obeyed in the decay of certain particles called K-mesons. Cronin and Fitch eventually received the Nobel Prize for their work in 1980. A lot of prizes have been awarded for showing that the universe is not as simple as we might have thought. There is a mathematical theorem that says that any theory that obeys quantum mechanics and relativity must always obey the combined symmetry CPT. In other words, the universe would have to behave the same if one replaced particles by antiparticles, took the mirror image, and also reversed the direction of time. But Cronin and Fitch showed that if one replaces particles by antiparticles and takes the mirror image, but does not reverse the direction of time, then the universe does not behave the same. The laws of physics, therefore, must change if one reverses the direction of time. They do not obey the symmetry T. Certainly, the early universe does not obey the symmetry T. As time runs forward, the universe expands. If it ran backward, the universe would be contracting. And since there are forces that do not obey the symmetry T, it follows that as the universe expands, these forces could cause more anti-electrons to turn into quarks than electrons into antiquarks. Then, as the universe expanded and cooled, the antiquarks would annihilate with the quarks. But since there would be more quarks than antiquarks, a small excess of quarks would remain. It is these that make up the matter we see today, and out of which we ourselves are made. Thus, our very existence could be regarded as a confirmation of grand unified theories, though a qualitative one only. The uncertainties are such that one cannot predict the numbers of quarks that will be left after the annihilation, or even whether it will be quarks or antiquarks that would remain. Had it been an excess of antiquarks, however, we would simply have named antiquarks quarks and quarks antiquarks. Grand unified theories do not include the force of gravity. This does not matter too much because gravity is such a weak force that its effects can usually be neglected when we are dealing with elementary particles or atoms. However, the fact that it is both long-range and always attractive means that its effects all add up. So for a sufficiently large number of matter particles, gravitational forces can dominate over all other forces. This is why it is gravity that determines the evolution of the universe. Even for objects the size of stars, the attractive force of gravity can win over all the other forces and cause the star to collapse. My work in the 1970s focused on the black holes that can result from such stellar collapse and the intense gravitational fields around them. It was this that led to the first hints of how the theories of quantum mechanics and general relativity might affect each other, a glimpse of the shape of a quantum theory of gravity yet to come. Chapter 6. Black Holes. The term black hole is of very recent origin. It was coined in 1969 by the Americans. The term black hole is of very recent. Chapter 6.
Okay, everyone, so we made it to chapter 6. We can finish we are a third of the way into the book. We are a little bit more than a third of the way in the book. We are 2 hours and 39 minutes in. So, you know, I was busy. I'm gonna rewatch all of this, and I'm gonna make a whole video about what I think about this book from listening to it on the audiobook. But I think it's really good. I just wanted to make a marker here because now I'm just gonna chill out for a bit. I wanted to tell everyone I'm extremely grateful for everything. I am so grateful. I'll never let my higher-ups down. I'll never let my bosses down. when I think of them, I think of succeeding for them. Like, absolutely succeeding for them, doing good for them. You know, I want to get fit. I want to take peptides, get immaculately fit, like get an Adonis body. I'm gonna get beaten up, guys. Right? Well, where'd that come from? I'm gonna get into fights. Really, I am. I want to be the best. It's like Pokemon. I want to be the very best, like no one ever was. To catch them is my real test. To train them is my cause. I have 3 main Pokemon that I always use. I have 3 main Pokemon and a Professor Oak. I have the Powerpuff Girls, and then I have Professor Oak. I have Totally Spies, and then I have Professor Oak. Can I be honest with you guys? Professor Oak is legitimately like the best. I know my sponsor isn't really Professor Oak, but you know, just for the sake of it, I just want to say I owe him everything. Without him, I would have none of my blessings, and I wouldn't have these women in my life. These women would not exist in my life. Without him, I would have ceased into the urban hell. I would have died of a fentanyl overdose. I would have been killed by a hate mob. And because I have him, I have every blessing that I could ever want. I can have as many children as I want. My bloodline is of a homunculus variety. Like, I'm all set. Other than that, I'm grateful for the women in my life. They come first. I have a beautiful redhead. She's absolutely gorgeous. She is everything you could ever ask for in a woman. She is everything you could ever ask for in a woman. I promise on everything. And then there's another one that I don't ever talk about, but she's special. There's another one I don't ever talk about, but she's special. But I'm already in daddy mode. Right, I'm already like, I'm ready to have these kids. Like, I just want to get my procedure reversed, and then I want to go forth from there and start going to college, go to Clearwater, get inclined with the best of the best in the entertainment and science industry. Go get inclined with the Shriners International. You know, these are all things that I want to do. I need to read books. That's why I'm doing this, is because I'm dipping my toe into audiobooks while playing video games. But guys, I have nothing to complain about. I have nothing to complain about. If I complained, that would be sacrilegious. Like, what kind of baby would I have to be to complain? I wanted to say, my record label, who I'm very loyal to, I'm in their brotherhood, you know, so I'll never do them wrong. I'll always do good by them, their boss. When I die of old age, I'm gonna die of old age when I'm 88 years old, when I'm 86 years old, and my son is taking care of me. When I go, my record label is going to inherit everything. My record label is going to inherit all of the music, at least. All of the music. So the goal is to make as much music as humanly possible, so that I can leave my voice, as I am forever to be praised, so I can leave my voice in their hands. If they want my voice for AI, then I'm willing to give my voice for AI. But don't forget, I'm always number one. I'm always grateful for what I got. Alright, believe it. I'm always grateful for what I got. I have no complaints on anything. My beautiful redheaded girlfriend, I would do absolutely anything for her. She's like my Bonnie. I'm her Clyde. You know, she knows I'm imperfect. She knows I'm imperfect, but I'm a steal. She knows that for sure. She knows I'm imperfect, but she knows I'm a steal. Because I too was a turkey waddling on the turkey farm, and so was she. And we got together and we turned into paradise pigeons. Not kidding. But other than that, guys, I'm so grateful for everything. I can't complain. I'm gonna let you all go for now. We finished it to chapter 6. We are 239:20 into it. Into the book. So we're doing good. The book is 5 hours and 41 minutes long. But yeah, it goes like that. I'm enjoying doing this series. Please stick with me for the future. Thank you.